that working? Yeah. All right. So you can take your law of cosines, and if you only know the sides of a triangle, right, you can still figure out the angles by starting off and figuring out one of them. And that first one we chose is A. So I rearranged that equation. Now I'm just going to plug in the numbers. A equals inverse cosine. All right, so what do I have? I've got little a is 8 squared. I'm gonna do these. 8 squared is 64, right? That's fairly straightforward. Minus b squared is 25, so 5 squared, 25, plus 100, divided by -2 times BC. So that's going to be 5 and 10. And if I take the inverse cosine of this, I'm going to get 52.4 degrees. So that's what this angle is. That's what A is. It looks like, yeah, you know what? It looks like I did the same thing. So now from here, you can use law of sines, right? Or you can just use law of cosines again. And I'll do angle B with the law of cosines again. Since that's kind of, we already did law of sines. But remember, law of sines is just A over sine A equals B over sine B equals C over sine C. So you could use this or law of cosine to continue. Now, I really only have to find one more angle, because once I find the other angle, then I just subtract the existing angles from 180 and I get the other angle. So let's go with B for angle B. This is the angle symbol. So now I'm writing B squared. So this B squared equals A squared plus C squared minus 2AC. Remember, the law of cosine is for two sides and the angle between them, right? So these are the two sides, A and C. This is the angle between them, and this is the opposite side, B. So I do the same math as I did up here, and I wind up with B as the inverse cosine of, again, B squared minus A squared plus C squared over -2 AC. And this just turns out to be, let's see, what are my numbers? I didn't actually put my numbers in. So that's going to be 25 what's A? A is so 64 plus 100 divided by -2. A is 8, C is 10. So B is equal to, in this case, 29.7 degrees. And then C, well, we know A plus B plus C is equal to 180 degrees, right? Because of the triangle. So C is just going to be equal to 180 minus, what do we got? 52.4 plus 29.7. Let me just draw an arrow. So C is equal to 97.9 degrees. So we can list them out below here if we want. 52.4 degrees, 29.7 degrees, and 97.9 degrees. Did anyone get different answers and not understand what I did?
My only thing is at the top of the page, it says round to the nearest degree.
Oh, yes, you're right. It does say round to the nearest degree. So see, I can't follow instructions. That was that was what I was supposed to do here. So yeah, this is A is equal to, right, that was the whole reason for me to rewrite them. So now I look at these, I'm like, A is, okay, 52, B is 30, and C is 98. Yes. So there you go. So the point of that, right? That's a good point. The point of that is you should read the instructions and see what's being asked of you. Now, if for some reason I asked you to round to the nearest degree and you typed in these answers, right? I'm not gonna mark them off. It usually depends on what what kind of mood I'm in on the test. If everyone's getting this wrong, I might take off a point. But usually you just get the credit for the. Don't report this out to like 7 digits, right? There's no need for that. Okay, so that is basically all the examples. The other thing I did for module 1 is in these slides, for chapter 1 slides, at the end here, there's some other helpful geometry, right? So this is all in your textbook, but I put it in here as well because I know, you know, some people like to have it in their slides. A equals C and B equals D if you have two straight line intersections, right? The opposite angles are the same. Here's your complementary and supplementary angles adding up to either 90 or 180. Some of the angles of the triangle, interior angles is 180. We use that. This is just a reminder, right? Straight line intersecting 2 parallel lines. A equals E, B equals F, C equals G. Oh, that's a typo here. Oh, no, okay. C, yeah, et cetera, right. Sorry, C does equal B, yeah. But the same thing, C equals G, D equals H, B equals C, A equals D. These are all the same. Similar triangles. Trying to remember, you will use this. Yeah, you'll use this with forces a little bit. Similar triangles, same shape, and they're proportional, right? We're actually going to use this in the context of force vectors, where if the force vectors make a certain triangle and you have certain measurements, right, the forces are proportional to the measurement proportions. But this also works for angles, right? Works for angles, it works for lengths. 1 radian. Oh yeah, 1 radian. You know, I don't know how much you're going to use this as much as you're going to use the actual radian, but it's basically the angle of a circle in which 1 arc length is equal to the length of the radius. So just notice, this is R, and the arc length is also R between these two. That's what a radian is. That's where it comes from. Circumference and area of a circle. Oh yeah, know this, guys. Circumference. Circumference is basically the perimeter, right? It's pi times diameter. Area is pi r squared, or pi d squared over 4. A lot of times you're going to be given things like diameters. We'll do this more in mechanics. You're going to have diameters of things like rods and stuff. if you're specifying a diameter, it really helps to use this formula. You'll see this formula get used a lot in engineering disciplines, especially like mechanical, aerospace. And what's this? An angle. Oh yeah, 1 radian. Yeah, this is just a definition of an angle. You guys know that a pi, right? Pi radians is a converts over to 180 degrees, right? So if you have degrees and you have radians, you need to transfer between them. I should add that to the to this list here. Okay, so that's module chapter 1. So what I'm going to do here is I'm going to start module 2, chapter 2. They correspond so far. So right now they're the same thing. Let me find my folder here. Oops, these are the videos I uploaded. Ah, in the wrong year. All right, so I'm going to open up chapter 2. The most time-consuming, well, it's time-consuming loading and putting everything in, organizing in Blackboard. So I still need to get ahead of myself a little bit. Chapter 2. So now we're going to take what we learned geometry-wise, and we're going to apply that to understanding vectors. And this chapter is all about vectors and forces and resultants. And a resultant, you're going to find out, is just basically the result of more than one vector acting, or more than one force acting on something. So vectors, we're going to start off with vectors. We're going to talk about forces. Then we're going to talk about how you can use vectors to represent forces. And then after that, how do you add forces or vectors together to get the result? So let's see, vectors, scalar quantities. I thought I had, no, I don't. Okay, remember, scalar quantities are things that you don't have size or magnitude associated, or not magnitude. You have size or magnitude, you don't have a direction associated with, right? So things like time, right? It took him 60 seconds to walk down the driveway. 60 seconds, right? Area, if I give you the area of something, right? There's no direction on that. I don't say I've got, I got 100 square acres of land to the left, right? It's just, I have 100 square acres of land. You can give a location, but you don't need to have a direction, right? You don't say I have 100, I guess you could say I have 100 acres of land northeast. Maybe this is a bad idea. Vector quantities, though, have magnitude and direction, right? Like velocity. Velocity of 60 miles an hour east. 20 newtons downward or 20 newtons upward. Acceleration, right? Depending on how you're defining what you're doing. 10 feet per second squared upward, right? Maybe you're launching a rocket. Acceleration of gravity is constant 9.8 meters per second squared down, right? And typically with vectors, you have some kind of, well, graphically they're represented with an arrow, right? And the arrow shows the direction. A lot of times the length is corresponding to the magnitude. There's some neat software out there, fluid mechanics software I've used, where you can ask the computer to plot the vectors of the fluid velocity, right? And you can ask it to scale the vectors all the same, or you can ask them to scale with the magnitude like they normally would be. And you can see the resulting magnitude of flow, right? The areas with really high flow have really long vectors. The area with really low flow has really small vectors, short vectors. How do vectors act? They have some kind of point of application, right? So you're applying it at some point, and then it's got a direction. it doesn't have to be vertical or horizontal. It can be any direction, right? And this is just a 2D, but in the more advanced classes, the vectors will go in 3 dimensions as well. So you have X, Y, and Z. And a lot of times we use vectors to represent forces because forces are acting on some object, right? You have either you have a rope tied to something, or something's moving on a track with respect to gravity, or just even free falling. But you have some kind of force acting on something in a certain direction, right? And sometimes you might hear the word sense. Sense is just a general term for the direction, right? So the point of application, the magnitude here is 10 pounds. The line of action, notice the vector itself is this red. The line of action is this dashed line. The line of action runs through the vector, and the vector can act anywhere along the line of action. And then the sense is basically the direction, right? So in this case, the sense would be 30 degrees from the horizontal, right? Positive 30 degrees from the horizontal. If you exert a force on something, right? You have to make some kind of contact with that thing, unless it's some kind of magnetic force or gravitational force. But if I'm pushing on something, right, I'm going to have a point of application. So say I'm pushing on this railroad cart, and I'm pushing at this angle, right? This is my point of action, and my magnitude is 20 newtons, right? And I have this thing called a line of action, which runs through this object along along the sense or the direction of this force. Now, before I talk about the second bullet, this is it's the same thing as if I was pushing here, or if I tied a rope to point B and pulled exactly along the same line of action with 20 newtons, it's going to give me the same result, right? It's the same 20 newtons along the same line of action. So that line of action represents where that force is acting along. And that force could be acting at point A, pushing, right, at that angle, or it could be acting at point B, sort of pulling along that same line of action. If I have a certain force and it's not enough to actually cause any motion, right? So maybe the forces of friction are high enough on this cart that the 20 newtons isn't pushing it, right? It's not starting motion. Then we have what's called static equilibrium. We say this is in equilibrium, it's in static equilibrium, it's not moving. Just think static, right? Static is stationary, not moving. This is the principle of transmissibility, which I just talked about on the previous slide. There's a separate slide for it, and it's important enough because when you do analyses of things with force vectors, for ease of analysis, you may want to slide the force vector along its line of action. And that's this principle of transmissibility, right? You can put this force anywhere along the line of action and it has the same effect on the body, right? It just maybe makes your math easier if you put it down here and there's another force acting to make force triangles. And we'll get into force triangles in a few minutes, probably. Here are forces in an angle. Typically, you're given either an angle or a slope. This is the same thing, right? 45 degrees versus a slope of 1 to 1. Watch your units. In the SI system, force is in newtons. In the US, it's in pounds, right? But do not confuse this with pound mass. This is why I think people have this problem, because in the English units, we say pounds. We use pounds for both mass and force, which is not really, we don't differentiate. In science and engineering disciplines, you'll sometimes see LBF or LBM, or pound force or pound mass, so that people recognize what that difference is, particularly if it's in a situation where the two could be, maybe both are being used, or they're used in the context, if you're not clear of the context. Remember, force is not mass. Newtons are not a mass, right? If I give you the weight of something, if I say something, or the mass of something, if I say something has a mass of 10 kilograms, right? Its force in the field of gravity, the force that's acting downward, is mass times acceleration, right? So in this case, it's the acceleration of gravity, right? Which is 9.81 meters per second squared, or 32.2 feet per second squared. Let's see. All right, this is good. Applied and non-applied forces, right? An applied force is something you you put directly on the object. That's fairly straightforward. Non-applied force is something like gravity, right? It's not directly applied to something, but it's still there. Now, with gravity is interesting. If you took a book, right, and you chop the book up into small squares, right, gravity is still acting on each of these squares, right? And what happens when we have a large object like this? Gravity is sort of acting on it, all over it. We tend to write the weight as this sort of a single arrow at the center of gravity of something. And we're going to talk about centers of gravity. Oh, I don't even remember what chapter it's in here, but later on in the course. But that's a simplification we make. We talk about the center of gravity of an object. Internal and external forces. We're going to talk a lot about external forces, and those are the ones that are applied outside of a structure, right? So, gravity, someone pushing, someone pulling. An internal force is going to be inside of a structure, and it's typically due to external forces, right? So there's multiple levels of internal you can think about. Think about, okay, your car is sitting on the curb, right? The force of gravity is acting on the car, and its point of contact with the external world are the tires, right? Well, and you can draw that. You can say there's forces acting on those tires due to the weight of the car. But then you can go and you can say, okay, well, the tires are attached to the axle, which is attached partially to, it's got this shock here. And you can figure out, okay, the force on the shock, right? That's one level of internal force. It's internal to the structure of the car. But now if we define our structure as the spring of the shock, right? Well, maybe we know the force, but then now we can go even further. We can talk about the forces inside the actual material. That's stress. That's what we're going to cover in mechanics of materials after this class. So MET 205 if you have to take it. Internal, external forces. This is typically what you're going to see in this class. You'll see tension and compression. You can have forces acting at angles. We're gonna talk about that briefly. Well, we'll talk about it with moments. But this is in tension. This force is acting along the central axis of the object, right? That's important. It's in tension, and this object, the forces are acting directly opposite of each other along the same line of action. This object's in compression. So that's those are the two extremes, tension and compression. Let's see. when you talk about external forces, you can have acting forces or reaction forces. In this picture down here, an acting force would be something like this 30 pounds, right? It's an applied force and it's acting on this structure. If I take this structure and disconnect it from the ground, I can see that in order to counteract this 30 pounds, I need to have, and based on the measurements and everything, you'll learn how to do this. I need to have 15 pounds of force, reaction force by the ground, right? This structure is supporting this extra 30 pounds, assuming the structure weight is negligible, right? There's a reaction force of 15 pounds at each of these points, right? In reaction to this applied force. When we take forces and we put them as vectors, we're going to talk about something called resultants. And a resultant is what you get when you take and add vectors together. And when I talk about adding vectors together, adding in the sense of you could be subtracting, right? Because vectors are going to have components. You're going to have forces that are additive, right? If I'm pulling, let's see, additive or subtractive, right? If I'm pulling oh, I can't even see my pen. If I'm pulling something to the right and I have another force pushing from behind, right? Those are additive vectors. If I've got two people pulling on either end, they're going to subtract and the net force is going to be lower. And again, we'll get into those details. Vector addition, right? So vector addition takes into account both magnitude and direction. So you could have forces that are acting in opposite directions. Here's an example, right? Here you've got an origin. Oh, this is a resultant. We've got, oh, I don't even know what's going on here. This is a double-sided arrow. It should be pointing, I guess, this way. So you go 4 kilometers this way, right? And then you go 3 kilometers back. The resultant displacement is this, right? 1 kilometer. I got to fix this drawing. Similarly, so this is in 1 dimension, right? And you can think about this as taking a walk. I walk 4 kilometers this way. I walk 3 kilometers this way. My result is that I'm 1 kilometer away from my starting position, wherever that is. You can also look at this in sort of 2D. Say this is, you're looking at it from the top down. And someone decides to run 4 kilometers this way, and then they turn down this street and run 3 kilometers down this street. Well, the resultant from their point of origin is, I mean, you could say go 4 kilometers east and 3 kilometers north, or you could say go 5 kilometers at whatever angle this is, right? And you can reach the same destination. So that's a resultant. It's a combination of vectors. And I know I use distance there. It applies to distance, it applies to forces, applies to velocities, anything that's a vector quantity, basically. All right, 3 methods of vector addition. Just looking to see if there's any questions in the chat. Nope. Graphical, analytical, and components. So graphical is where we take these arrows, and we'll just go through them. If you're doing graphical, the vectors have to be drawn to scale, right? And typically, I guess true graphical is where you use some kind of graphical paper and or a ruler, right? You're taking measurements and you're measuring angles. And typically here you're going to be given things like angles and lengths, and you're just going to have to figure them out. But you can use a few things like the triangle rule, right? Triangle rule is used for 2 vectors, and it doesn't have to be a right angle triangle. So you can see where things like the law of cosine will become important, especially if you have vectors that are not at a right angle triangle, right? We've got to be able to figure out lengths and angles without the Pythagorean theorem. Parallelogram rule, this is another way of analyzing two vectors. And then we've got this vector polygon rule. That's used for more than two vectors. All right, vector addition, tip to tail, and approximate scale. Oh, it rhymes. And then we're going to use trig to solve the mathematical functions. Do I have an example? Oh, here's the example. So the first example is this: determine the resultant and indicate the angle or slope for each right angle force system shown. So I've got these four force systems, and we're going to go ahead and solve these. The first one here, I've got 2 pounds to the right and 3 pounds acting down. So there's something here, and you could think, okay, maybe this is a nail, right? I've got, I'm hanging something off of it this way, and there's also 2 pounds exerted on it to the right. So what's the resultant force on that? So let's go into this. All right. So for part A, that's this one here. Let's see, which one did I do? Tip to tail, parallelogram. Yeah. Either one, I guess, works. All right, let me sketch this out. I've got 3 pounds acting downward. And this 2 pounds here, I can take this vector for the sake of addition and I can move it around. This is basically, the parallelogram rule tells us that you can basically take this vector setup and draw it as a parallelogram. In this case, it's just going to be a square like this. And the resultant looks like this. Oh. It's our resultant. This is a triangle. This is 2 pounds. It's 3 pounds and 2 pounds. And all I did is I made a rectangle out of it, right? And I can see I've got a right triangle in the middle of this rectangle, which is the diagonal for these forces. You could also think of this as, at this point here, the 2 pounds is pulling on this point, and the 3 pounds is pulling on this point downward. You can also think of it as the point over here is the 3 pounds is pulling on it downward, right? And the 2 pounds is pushing on it to the right, because pulling to the right with 2 pounds and pushing to the right with 2 pounds is along the same line of action, right? And that lets you make this triangle like this, 2 pounds and 3 pounds. So what do you do when you have a triangle like this? You can figure out R using the Pythagorean theorem. So we see here that R is just the square root of 9 plus 4. So the resultant here is, what does this turn out to be? 3.61 pounds. So that's the resultant. The next thing we have to do is, what's the direction, right? The angle. There's a few different ways to specify this. I'm going to look for the angle here. And I'll call this theta. Now I can use a few trigonometric functions. I already know what the length or the magnitude of R is, but I can use the tangent function as well. So remember, tangent of theta is going to be opposite over adjacent. So this is going to give me an equation that theta is inverse tangent. What's the opposite? It's 3 over 2. And so my theta here becomes 56.3 degrees. So I can say R is 3.61 pounds. This is R the vector now, right? And it's acting at, and this is where angle notation is much easier writing than on a computer, 56.3, because I don't know that these symbols all exist. I know one angle symbol exists pointing basically upward. But I can denote my angle from the horizontal, right? I can say it's 56.3 degrees off of the x-axis horizontal, right? And that's my resultant. My resultant is 3.61 pounds acting 56.3 degrees down from the horizontal. Does that make sense? Well, let's think about this, right? If these two forces were equal, I would expect a resultant equally between them, right? 90 degrees, so it would be 45 degrees on either angle. I've actually got a smaller force acting horizontally than I have doing vertically. So I would expect my resultant's going to be skewed more towards a smaller angle in here, which means a bigger angle in here, greater than 45, and that's that 56.3. So that makes sense. All right, the next ones, once you do one, the rest are fall into place here. I'm going to redraw B just probably how I should have redrawn A. So B has got these two forces acting at a point, and you can say this one's acting to the left at 10 pounds, this one's acting down at 22 pounds. I'm going to draw them so that I still have 22 pounds acting downward, but I have the 10-pound arrow acting to the left, pushing instead of pulling, right? Again, because of the transmissibility effect, it doesn't matter if my force is pushing with 10 pounds to the left or pulling with 10 pounds to the left on that point, right? It's the same, idea. So I've drawn this vector triangle, and now I have a resultant that looks like this. I'm connecting my vectors. This is the tip to tail method. So the tip of this vector to the tail of this vector. And you connect your vectors up, and then you can draw your resultant between them. Think about it too, as if you were walking, right? Forget the force. You start here, you go this way, your resultant is you've gone that way. Same thing with force. You pull this way with 10 pounds, you pull down with 22 pounds, your resultant is going to be somewhere in between like that. So let's put resultant, and let's put theta here. And again, we do the same math we did before. R is going to be the square root of each of these, the sum of the squares. So here we've got 100 plus, oh, what's 22 squared? Oh, 484. I did write it down. Good. So this is going to be 24.166. I'm going to leave that for now. The angle theta, right? Let's use, let's just use cosine. Cosine theta is adjacent over hypotenuse. So the theta is going to be the inverse cosine of Adjacent is, in this case, for theta, adjacent is 10 pounds. And we've got, I'm going to use the square root of 584. When you're doing this with a calculator, it's good to carry more decimals. You could stick in the 24.166. And you wind up with theta equals 65.556 degrees. So let's write this out. The resultant is, oh, wait, just in time here, 24.2 pounds, right? So I'm rounding now. And it's acting at 65.6 degrees below the horizontal in the negative, this is basically the negative x and negative y direction. But that's why it's so nice to be able to write this stuff, because you can denote a lot with just an angle symbol. Otherwise, if you're talking about just an angle from the horizontal x, right, you're going to have to translate this into something more reasonable, which is 65.6 plus 180. So this is at an angle of 245.6 degrees. So there's different ways you can report this, right? You can report it using these symbols which show you visually the direction, right? Or generically, when you report an angle off of the horizontal, you typically report an angle from the positive x direction, right? And this is the standard sign you'll see. In fact, if you look hard enough, you can find this program in the computer somewhere. And in this case, it would actually be 245.6 degrees. These are the same angles, right? It's just one is reported from the positive horizontal x-axis. This is reported from the negative horizontal x-axis. And you can see that by the graphic. So that's where we'll leave off, and we'll pick up here on Friday. Any questions about anything there? But hopefully you can see